the year 2022. So this is a very special lecture. Good. Okay, so any confusion so far, whatever we have learned in the sine triangle? So some more details we will understand about sine triangle PWM. This is something very common. You all do in your daily simulations. But the understanding what should be there, perhaps it is missing somewhere. So I am trying to go into the details of what you might not have noticed earlier. So first thing is that getting how the modulating signal and the output voltage are related, how that is derived. So this is what we have done first. We have taken the duty ratio, which is actually responsible for operating or giving the output voltage, taken that as the basis, and we have derived the relation between the modulating signal and the output voltage. And this is pretty linear relationship we are getting, right? So we have something like this, the modulating signal given as the sinusoidal waveform with amplitude m. So m is called the modulation index. Now here this is different from what we have seen in the low switching frequency case because we have a different PWM. Then we derived and we are finding that the average pole voltage per switching cycle is basically related like this, or half switching cycle is related like this. So what is true for half switching cycle is also true for the full switching cycle and hence for the entire waveform. Why I call it half switching cycle? Because see, this switching is started from on state and it is ending at off state. So there is only one switching involved over here. And that's only half switching cycle. You understand the point? What is full switching cycle? If it is starting from on, it should end up at on state, or vice versa. If it is starting from off, it should end up at off. This is full switching cycle. Correct? So full switching cycle is basically realized. We have seen that this triangular wave is actually good for having reasonable switching in the converter rather than having the ramp type of signal which we use for DC-DC converter, because we have multiple phases over here. So whenever we are dealing with multi-phase system, we should have this kind of, or at least more than one leg. Whenever you have, we should have this triangular carrier kind of carrier. So triangular kind of carrier for comparison with the modulating signals or reference signal. It is not bad to have this carrier in the DC-DC converter also. This is applicable there as well. There is no problem in that. Now, when you have this full waveform, here we will have, this is one carrier cycle, right? And here if you see, the R phase is starting from on and ending at on. So this is one switching cycle you are completing. Similarly for B and Y and B also, you are completing one switching cycle. Wherever you started with, you are ending with the same state. So hence the carrier frequency is basically same as the switching frequency for two-level converters. You understand the point? So if I write FCRR as the carrier frequency, the switching frequency is exactly same as that. So per carrier cycle, we are having one switching cycle. That's what we are seeing over here. Sometimes this half carrier cycle, this portion half, is also called as subcycle or half cycle, because any analysis what you do in this half or this one subcycle is basically correct for the complete waveform, the entire range of, or the entire cycle of the fundamental signal, because it is true for the next half also, and the same thing is repeating basically multiple times within the fundamental cycle. You understand the point? Yes or no? Say something.
Yes, sir.
So yes, sir. This is what we are observing. So we have seen that if we have to realize a converter using sine triangle PWM, and we are operating a system which is having output voltage of, which is having, let's say, a rated input voltage of 400 volts. So we need to have this much amount of DC bus voltage in order to fulfill the requirement for the load in terms of voltage. So basically this VDC by 2 is your peak phase voltage. This is what we have seen. So we cannot get more than this in terms of the peak phase voltage whenever we are using sine triangle PWM. And please note that this is purely sinusoidal modulating signal. We have not injected anything extra in that. We will discuss those things little later, maybe after a couple of classes. So this is what we are arriving at. And this number 653, what we have got is fairly higher than what we were getting for the low switching frequency PWM. So obviously the utilization for DC bus voltage is more for low switching frequency PWM, and it is lesser for the sine triangle PWM. For sine triangle PWM, it is only 50%. And for the other PWM low switching frequency, we have something nearly like 63% or so it is there, right? Ashish?
Yes, sir, it is.
So this is what we see the difference between the two. Now we will see some more differences between the two PWMs, what we have learned so far, and some characteristics about what we should see in the sine triangle PWM, what we should expect. Now the PWM, what we have learned in the low switching frequency case, we are giving some notches. No, let's say this one notch we have given in one quarter cycle. So we have two switching angles per quarter cycle. And then another notch is given in the next quarter. And then this half cycle completes. So there is another notch in the third quarter, and then another notch in the fourth quarter. Like that it goes, right? Correct?
Yes, sir.
So what we are doing basically, we are realizing the fundamental voltage in terms of these switching angles. We have related our fundamental voltage as function of alpha 1 and alpha 2. And we are realizing in that manner. But if you observe closely a little bit, what is happening basically, the width of these pulses are effectively getting changed when we are realizing this fundamental component of this. So higher the fundamental component, higher this width should be, the positive, and same way during the negative pulse should be higher. The width should be more. Obviously, this is somewhat like our fundamental component. It is going to be like this. So if you want to achieve higher, we need to have wider width for the positive during the positive half cycle and wider width for the negative during the negative half cycle. This is general understanding, right? And this is what we say the pulse width modulation. We are changing the width and not the DC bus voltage to attain different. We are not going by this method, changing the DC bus voltage for the same alpha 1, alpha 2, but we are changing alpha 1, alpha 2 for the same DC bus voltage, and we are realizing the fundamental component. Something similar, but little bit more systematic, we are trying to do in our sine triangle PWM. So what we have basically, okay, let me go to new slide, that is better. So a lot of questions what you have in mind will be answered today. So what we have basically, we are trying to compare, let's take only one phase because all others can be seen in a similar manner. So let's have just one phase. This is the carrier subcycle, and we are having, say, our modulating signal is having a magnitude somewhere like this, let us say. Correct? Some value around 0.4 or so. Only one phase we are analyzing now, so that's okay. Now in response to this modulating signal, what happens? We generate our gating signals, or you can say the pole voltage output. So how the pole voltage output will look like? It will be a pulse of, say this is 0 axis, of this much width on the positive side and small width on the negative side. Correct? Now, as you change this, let us say you come down this modulating signal value to this point, say 0.1. So what will happen? The positive pulse, let me draw in blue, will change to a lesser value. and negative will increase. Understanding my point? Then if you try to realize a zero voltage, what will happen? There will be equal width for both. Say, for example, here, equal width for positive and the negative. You understand the difference? So now what is happening? The width of this pulse, you can say, is changing with the value of modulating signal. You understand? Now, in one cycle, what we have basically, our modulating signal is changing its value from 0 to some peak value and then coming back to 0 and then going to negative peak and coming back to 0. This is how typically the sinusoidal modulating signal is. So what we can expect that if you see the PWM voltage near the zero crossing, it should have equal width. So it will look like something like a negative here and a positive here of equal width. This is the switching cycle. In sub-cycle we can say TS or TS by 2. Half of the switching cycle if we take. So this is what we will observe. And this will be true for every zero crossing. Here also if you observe how it will be, it will have equal positive and negative. And the reason is because we are realizing a zero voltage. So average voltage of these two should be 0. Understanding my point? Now, how it will be during the positive peak? Now you can guess, right, how it should be. Someone?
Positive half will be maximum and negative half will be minimum.
No, maximum minimum is okay. But what will happen? The width of this
on time will be more, sir.
Yes. By maximum, I think you mean the width of this pulse, right?
Yes, sir.
Yeah. So width of this positive will be maximum near the peak. Now, if you have modulation index of 1, which means what? Your modulating signal is actually sitting here at the top of the carrier. So what will happen? There will be only constant positive and no zero, no negative. You understand my point? This is the maximum limit. No, we are realizing VDC by 2 peak value. For any intermediate value, which is m is less than 1 and of course greater than 0. So we have this kind of width. So it is changing. Let's say here it was 50-50 and gradually it increases and reaches to a say 80% positive or 90% positive and no rest of the things negative, like that it will reach. And then gradually it will reduce again to 50-50. Then when you reach the negative peak, how it would be? The positive will be smaller and negative will be much wider. You understand the point? And then again it will go back to 50-50. That is how the pulse width will look like for the entire cycle. And this variation what you are seeing in the positive width or negative width, this is happening in a manner of sinusoidal waveform, because we are trying to realize the sinusoidal waveform over here. So this variation would be in a sinusoidal manner. You understand the point?
Yes, sir.
Yes, sir.
So this is what we observe. Now, of course, this is the nature what I will show one example also. So this is what we are observing, but we also need to know a little bit like what should be the carrier frequency or switching frequency suitable, which is like giving the best performance for the sine triangle PWM. You can have any switching frequency. Yes, no problem in that, because all these are very, very high. This is very, very high compared to the fundamental. But the problem would be that some of the things we can make further better for sine triangle PWM if we maintain certain rules for this. You understand the point? Now, we understand that we are having a pole voltage which is having, let's say, 50% duty ratio, which is slowly going into some higher positive width and then gradually coming back to 50% again, then again going to some 10% only width, let's say, and then coming back to 50%. One thing which must be there in this whole PWM waveform is that to have, let's say, a fixed fundamental frequency, it should repeat itself after every fundamental cycle, which is what we have seen in case of low switching frequency also. Understand my point? If it does not repeat, then what will happen?
Sir, subharmonics.
Yes. So first condition, again Deepak, you are missing from the screen. Why? That's all. I got busy in teaching, so you are off grid. Please be there. I need to see your faces, no? That gives me feedback how it is going. Okay. So if it does not repeat, then we know that there are going to be subharmonics. But many a times, no, whatever we have seen for low switching frequency case, here any such thing is like very small in magnitude, very small maybe in number. So many times this can be ignored. Okay, it's a very small, let's say 1%. Let's say if you have a switching frequency of something like 3000 hertz and you are trying to run 50 hertz motor. So what will happen? You will run the frequency from all the way from 0 to 50, right? So some places it will match. The ratio will be some integer. Say for 30 hertz, for 20 hertz and all these things, it would be integer. But some places it will not be. Say for 23 hertz, this will not be an integer number. The ratio between the two, right? So what this ratio is called, when we know that carrier frequency is same as switching frequency. So this ratio is called some number, some name we have given, right?
Sir, pulse number.
Yes. So this pulse number is basically a ratio of carrier frequency and fundamental frequency in case of sine triangle PWM for two level voltage source inverter. So this pulse number may be integer, may not be integer when you are running from 0 to 50 hertz. Depending on how the ratio is coming out, you have constant switching frequency sine triangle. Understanding my point? However, because we are dealing with such large gap between the switching frequency or carrier frequency and fundamental frequency, the amount of subharmonics or any other unnecessary things may be very small, can be ignored. Understanding my point? However, it is always recommended that you have a repeating pattern for the PWM waveform. So then what should be the pulse number? It must be an integer. At least an integer always. Let us say you fix any number. Say here it is something like 60, right? So you maintain that. Doesn't matter. Now, next condition when you try to impose that, okay, I am having integer pulse number, but there was one more condition. So this is fulfilling the full wave symmetry condition. Now, there is one more condition which we should fulfill in general, right? So that can avoid a large group of harmonics, so which is half wave symmetry. So what was the condition for our low switching frequency for the pulse number?
Even odd.
Yes, it should be odd integer. You remember, right, all of you? Or forgetting slowly? Yes or no? Say something. Am I audible to all of you?
Yes, sir.
Yes.
So we have seen that pulse number must be odd integer if we try to maintain half wave symmetry. Definitely if it is even integer, you can never maintain. That's certainly there. Only if this is odd, you can have the possibility of maintaining half wave symmetry. What will half wave symmetry do?
Eliminate even harmonics.
Yes. So even harmonics would be missing from the waveform. So this same thing is applicable for sine triangle PWM as well. If you maintain a triangular carrier frequency, which is like say FCRR by F1 is something like P, and this is odd integer. So instead of 60, if you say 61 or 59, this is good number compared to 60. Because you will get rid of even harmony. That's not much difference, right? If you talk about 50 hertz carrier, what is 59 pulse number? What will be the carrier frequency?
2950.
And what will be 61?
3050.
Correct. The difference is only 50 hertz between the three frequencies. But what wonders it can do is that for this you will have even harmonics. But which order even harmonics, that we will see. However, these numbers will not have any even harmonic. Now when I say even harmonic, I do not mean second harmonic, fourth harmonic and all that. No, that's not applicable here. I'm talking about some higher order that I will come shortly. So, but the difference would be that just by keeping this kind of ratio instead of even number, you will get rid of a set of harmonics which are called even harmonics. You understand my point? So this is second condition which we are having for our pulse number P. Now we have seen for low switching frequency that once we maintain these two things, then rest of the things are basically maintained by our switching angle itself. So whatever switching angle alpha 1, alpha 2 we are having in one quarter cycle, we will maintain the other quarters with respect to this. In order to have something called as quarter wave symmetry and then three phase symmetry, what we will do? We will keep the angles in that manner. The rest of the angles are dependent on these two angles. And if this is VRO, VYO is basically VRO shifted by 120 degree. And VBO is basically VYO shifted by 120 degree. You understand my point? So the condition of three-phase symmetry and quarter wave symmetry are maintained forcefully. There is no condition on the pulse number or anything. This we are maintaining forcefully. We are saying that yes, we will shift everything forcefully by 120 degree so that we maintain three-phase symmetry. We will have uniformity across the peak of this fundamental component so that we have quarter wave symmetry. These things are forcefully maintained, right? We do not have such liberty in sine triangle PWM because here what we are doing, we are comparing three modulating signals MR, MY, MB with the same carrier. And we are generating the pole voltages VRO, VYO, VBO. The result is only comparison with the same carrier generation of these. Understanding my point? So there is no way that we can force that, okay, if we have generated VRO, we will shift it by 120 and generate VYO. Or we will shift this VYO by 120 and generate VBO. No, we cannot say that. This is now out of control for us. So we should have a mechanism here itself to maintain this three-phase symmetry at least. You understand my point? The mechanism is that whatever carrier is given to MR, whatever manner it is given to MR, or with respect to MR, whatever way you are seeing the carrier, it should be same for MY as well as MB. Do you understand my point? Partially or fully? Okay, let me put the condition straight. If you maintain P as odd triplet number, say for example 3, 9, 15, 21, 27, 33, etc. These are all odd triplet numbers. If you keep the pulse number or ratio of carrier frequency and fundamental frequency, the way MR sees CRR or the carrier is same as how MY or MB would see the carrier. Okay, I will come to this with an example shortly. If we do not maintain this as odd triplet number, No, as general odd number, let's say 7 or 11 or 13 or 17 something, then what will happen is that the carrier would look different for MR, MY and MB. I know, difficult to digest. Let us see. Let us take an example. So result would be that we will be maintaining three-phase symmetry. Now let us try to see. Okay, first let's have the pulse number 9. Okay, I don't know which one is there. Yes. So this is for single phase, right? This, for simplicity, I have taken pulse number 9 because it's clear a little bit here. Correct. Now what we are having 9 cycles of the carrier within this fundamental cycle, which means about the half, whatever is present over here is present over here. You just need to reflect it about this axis. You understand my point? So that is how we are maintaining the half-wave symmetry. We have seen that, right? Now, when you have this kind of pulse number ratio for all three phases, then now notice the point what I was saying. You have the R phase, which is matching with carrier 0 crossing here. You see that point? Now it is matching with carrier 0 crossing here, and it is matching with carrier 0 crossing here. Correct? Y phase also, if you observe, it is matching the 0 crossing here, matching the 0 crossing here, and so on. Everywhere it will match. So what is happening at this point? The carrier is going down and coming up. Here also going down and coming up. Even B phase also, if you see the positive 0 crossing, it's going down and coming up. This is what I mean by the way MR, MY and MB are seeing the carrier. It looks common to all three of this. Now you would wonder what will happen if I don't have this odd triplet number. Okay, let us see one example. And for clarity, I will keep a smaller number, say 7. Now look the difference yourself. I have synchronized the carrier with respect to the R phase. 0 crossings are matching, but do you see the same thing with the Y? This is pulse number 7. Do you see the same thing happening with B?
No, sir.
This is what I mean by how the modulating signal sees the carrier. Now it's different carrier for R, different carrier for Y, different carrier for B. The way it is oriented. So obviously the pole voltage which will be generated by RYB, they will not be shifted by 120 degree. They will be shifted somewhere here and there. You understand my point?
Yes, sir.
Yes or no?
Yes, sir.
Yes, sir.
Now why it is happening? Simple explanation is that when you are having carrier frequency, let us say if for simplicity you take only the fundamental component of this carrier FCRR and do the Fourier analysis, what you will have basically something like sine n omega t kind of waveform is there, right? Which is interacting with the other carriers. I'm doing the Fourier analysis, so only fundamental component I have taken, which is very crude simplification of that. But this number n, if you have something like 3 or 9 or 15, if you shift by 120 degree, it repeats itself, right? That we have seen as the common mode. Whereas if you have something like 7, 11 or any other number, for 120 degree shift, this will not match. You understand the point or not?
Yes, sir.
So the tendency for carrier to repeat itself for all the modulating signals will be there only if this pulse number is maintained as odd triplet number. If you go for just odd numbers, say 7 or 11, this kind of shifting would be there within the modulating signals with respect to the carrier. So in this case, when we have or triplet pulse number, we can say that VRO, VYO, VPO, these will be having balanced three-phase system. Or better, we should say VRN, because there will be some common mode which is getting cancelled. So VRN, VYN, VBN, this would maintain a balanced three-phase system. Understand my point? Which is not true in this case. So the conditions on pulse number, we have understood that it should be integer first. The foremost condition should be, it should be integer. Then it should be odd integer if you want to get rid of even harmonics. Now if you want to get rid of the triplet harmonics or triplet harmonics, you should maintain three-phase symmetry, and for that the pulse number should be odd triplet pulse number. So the options when we are operating sine triangle PWM, we have only limited options for the carrier frequency with respect to the fundamental frequency, or in other words, the pulse number. The options are 3, 9, 15, 21, 27, 33, and so on. You keep going. The number which is divisible by 3 and odd. That is the option available for sine triangle PWM. Any other number if you operate, you will encounter a worse performance compared to this, what these numbers can give. So if you have the option that you are going to make the carrier frequency 60 times, so I would recommend that don't go for 60, but go something like either 63 or you go for 57. These are better numbers. The switching frequency may not be very different, but the amount of improvement this will give in terms of harmonic, that will be much better. You understand the point?
Yes, sir.
Yes, sir.
Good.
Yes, sir.
Now, how about quarter wave symmetry? So far, we have not discussed anything about quarter wave symmetry. In general, sine triangle PWM, we do not worry about quarter wave symmetry. Why? Because there are so many carrier cycles coming within the fundamental cycle. Even if the quarter wave symmetry is not maintained, the disturbance, what happens when we don't have quarter wave symmetry? First question is that, do you remember what happens? We will have phase shift in the fundamental component, right? Or in fact, in all the harmonics. You remember, right? Or you are forgetting all that? Keep revising, please. That's why I asked you to keep your camera and mic, both things on, so that I can interact. And that will force you to revise all the things which I am teaching. You remember this part?
Yes, sir.
So phase shift in V1 is basically avoided when we have quarter wave symmetry. Now here when we have, let's say, 50 cycles or 100 cycles, the phase shift, even if you don't maintain quarter wave symmetry, could be very small, say 0.01 degree or 0.1 degree or something. All these are insignificant, may not matter at all, right? So that's why it's not very strict that you should maintain quarter wave symmetry in case of sine triangle PWM. However, if you do want to have all the symmetries in the waveform, the recommended way for carrier is this. Start the carrier from the zero crossing and go down. Always. Instead of starting from the peak value or maybe from the negative peak, all these things, start with the zero crossing which is going down. So if you maintain odd triplet pulse number for all the waveforms, it will look like this only, going down at the positive zero crossing. And this will certainly ensure quarter wave symmetry as well. If you have any other orientation, see, carrier can start from here, it may start from like this, it may start something like this. Correct. So any of these will basically, this may still give, but certainly not this orientation or any other. So best orientation, what I would suggest to maintain quarter wave symmetry and little bit better quality, is having this kind of carrier, which is starting going down. Fine. Now,
Yes.
when we have understood these things, then how the voltage spectrum or harmonic spectrum would look like for sine triangle PWM. So first, let us again go back to our low switching frequency PWM. We compare with everything with that. Let us say how the spectrum would look like if these are your harmonic numbers. So how it would be? There would be a fundamental with some magnitude. Then what other harmonics you would see in this case?
Sir, fifth,
Fifth,
seventh,
seventh, then
11th, 13th.
and so on. It will keep going, right? So you have these numbers available in the system 5, 7, 11, 13, 17, 19 and all that. Whereas if you are running with sine triangle PWM with sufficiently high switching frequency, the spectrum would look different. Here it's kind of continuous spectrum. No, you have fundamental and you have all others coming over there, all other components. So because we have half wave symmetry, even harmonics are missing. We have three phase symmetry, so triplet harmonics are missing. So rest of the non-triplet odd harmonics are visible in the spectrum. Whereas if you have sine triangle PWM, we will see a spectrum which will be very discrete. In a manner, there will be fundamental, and then after a large gap, you will see some harmonics appearing. And this generally appears around the switching frequency. Then you will have repetition of another set of frequencies around 2FSW and so on. It may keep going. So there will be huge gap between the fundamental and the other harmonics which would appear in the system. So when I say when you don't maintain the half wave symmetry in case of sine triangle, which even harmonics you would see? You would see even harmonics in this set. That also may be sometimes harmful when we are talking about the grid code or something. Some restrictions are there over how much even harmonic you can inject in the system. Whether this even harmonic is as low as second order or fourth order or something like 52nd order or 100th order. You understand the point? So difference between the two spectrum would look like this. One spectrum is continuous, which is low switching frequency. Another spectrum is kind of discrete. It has fundamental, then switching frequency band at or around switching frequency, then double of switching frequency, 3 times of switching frequency, and so on. It will keep going. Now, if you maintain even harmonics and three-phase symmetry and everything, this half-wave symmetry, three-phase symmetry, everything, sometimes you may see that from the spectrum, this may be missing. It may look like this, blank kind of. So which means that this was the common mode which got cancelled in the line-to-line voltage. You will observe when you do experiments or simulations and try to see the harmonics, this kind of thing you may see. If you have maintained three-phase symmetry, this is common mode which will get cancelled. You will have only side bands coming over there. You understand my point? Now, coming to the question which Deepak asked earlier, what is so special about this number 21? Now you must have guessed, we don't have much options first of all. What we have 3, 9, 15, 21, 27, 33. These are discrete numbers. And we are talking about getting a spectrum which will look like this. There will be fundamental, then discrete switching frequency spectrum, then double of switching frequency and so on. So to ensure that we are getting this kind of spectrum, our pulse number should be high. But what is the definition of high? Certainly if you have pulse number of 3, you are going to see this kind of spectrum rather than this. Even for 9, you will have this kind of spectrum. 15 could be somewhere in between. So that is how we arrive to the number 21, where we will have discrete spectrum, fundamental, switching frequency, double of switching frequency, and so on. So that is why most of the textbooks, they give the pulse number of 21 as the boundary, that okay, if you are trying to operate with sine triangle PWM with reasonable performance, you maintain this, because these numbers are discrete. The next number is 27 or 33. So once you have crossed the 20 times of the fundamental frequency, fine. You will rarely encounter any low order harmonic, or you should not encounter any low order harmonic. You understand my point? Deepak, is that clear now?
Yes, sir. But one part is clear, but now for like some of those like net move, they also state that like they
Your
compare
voice
with the
is-
synchronous PWM and asynchronous.
Your voice is not clear at all.
So I was telling that this with respect to synchronous PWM, it is clear, but even for asynchronous PWM also they are using the number as 21.
Huh, that is true.
But in asynchronous PWM again, whatever assumptions we have made, those will not be applicable because the quarter wave symmetry will be lost.
That is true, but there has to be some boundary, right? We generally say that if your switching frequency or something, it at least say 20 times of the fundamental, which means what? This kind of discrete spectrum you are going to get, which means you have 20 switching cycles within one fundamental cycle. Anything lesser, you will have something mix of these two. There may be some harmonics appearing on the higher side, which are on account of low switching frequency kind of thing. So this boundary is generally coming, which is like general understanding. And the number what we have next is basically 21. See, in case of asynchronous sine triangle PWM, we don't have any number. You understand my point? The word asynchronous means that there is no relation between the carrier and the modulating signal frequency. There is no synchronization. And generally the understanding is when we are running asynchronous PWM, keep the pulse number something like 100 or 50 or so. Do not come down anything below this. Then you will have discrete kind of thing. But at least you try to maintain this ratio, even if you are running with asynchronous, at least. And so the suitable number which is given to have, let's say somebody wouldn't say that you run with 20 times of the fundamental, because certainly you are going to encounter even harmonics. So why would someone take that risk? Then tomorrow you will blame that, okay, you have suggested me to run with 20 times and it is having so many problems. The grid code is not complied and all these things are happening. So that is why they would say, okay, make it 21. You understand the point?
That's the point is understood. That is clear.
So some things are understood practically. These things like if you go too much into analysis and getting which harmonic, how it is coming, no Fourier transform, double Fourier transform, and all that, you can get some mathematical explanation. But you should be able to feel that yourself. Just by looking at the waveform, you should get the feeling, yes, whether it is going correct or not.
Yes, sir.
This is what I am talking about.
That is there because okay, we go more than 21 only, but
Clear?
yes, that is clear.
So some understanding about sine triangle PWM is now clear to all of you. What we are trying to do, how we are trying to do, how to
Yes,
generate the triangular
Yes,
carrier.
sir. Yes, sir.
Good, good.
Yes.
Now, another important part which is related to analysis of sine triangle PWM. Basically, how do you check the performance of sine triangle PWM. This is what we will discuss tomorrow. Okay, because for anything we need to know how it is performing. If you cannot say that, then there is no point in saying what PWM you are having. You need to be able to gauge the performance of the PWM. You should be able to gauge the performance. Okay, so then I stop over here and